Hello everyone. Now that we've finished with the role of the data and the algorithm, and also we matched them, so we know that we cannot exist without data and algorithm at the same time. So we rely on them at the same time as well. We can continue with the hardware that we need to be able to build our server, our AI as well, if we would like to. Not just we, but of course, many companies need to consider this part, and that's why we talk about this here this time. So, if you really want to work in a field that is related to AI in the future, then yes, you should also know a little bit about the specialized hardware that is used in AI systems. Good, let's jump in. So chapter 4 this time, chapter 4. Now let's continue. Again, this is our book. It's about AI for Dummies. So Artificial Intelligence, the third edition, written by John Paul Miller, Luca Massarone, and Stefania Diamond. And now if we continue here with the specialized hardware. So understanding the hardware behind AI is critical for understanding its full potential. As AI advances, the technology supporting it should evolve to meet increasing demand. This time we will explore how AI hardware has evolved, starting with general purpose components and advancing to specialized processors tailored for complex AI applications. Let's start with relying on standard hardware. Most AI projects you create will at least begin with standard hardware because modern off-the-shelf components provide significant processing power, especially when compared to components from the 1980s, when AI first began to produce usable results. Consequently, even if you can't ultimately perform production level work by using standard hardware, you can advance far enough along with your experimental and pre-production code to create a working model that will eventually process a full dataset. We will start examining the standard hardware that is used. The architecture or the structure of the standard PC hasn't changed since John von Neumann first proposed in 1946. All these systems use the von Neumann architecture because it provides significant benefits in modularity. Reading the history tells you that these devices allow upgrades to every component as individual decisions, allowing increases in capability. Well, for example, within limits, you can increase the amount of memory or storage available to any PC. You can also use advanced peripherals, and however these elements connect through a bus as well. The PC you use today has the same architecture as devices created long time ago. They are simply more capable. In addition, almost every device you can conceive of today has a similar architecture despite having different form factors, bus types, and essential capabilities. We need to talk about the deficiencies as well. Von Neumann bottleneck is the first one. Of all deficiencies, the von Neumann bottleneck is the most serious when considering the requirements of discipline lines. such as AI, machine learning, or disciplines such as AI and machine learning, and even data science. You can find this particular deficiency discussed in more details later as well. Here, the limitation computer architecture, where the data transfer rate between the CPU and the memory becomes a performance bottleneck. We continue with the single points of failure. Any loss of connectivity with the bus necessarily means that the computer fails immediately rather than gracefully. Even in systems with multiple processors, the loss of a single processor, which should simply produce a loss capability, instead inflicts complete system failure. The same problem occurs with the loss of other system components. Rather than reduce the functionality, the entire system fails. Given that AI often requires continuous system operation, the potential for serious consequences escalates with the manner in which an application relies on the hardware. The third one is single-mindedness. The von Neumann bus can either retrieve an instruction or retrieve the data required to execute the instructions, but it cannot do both at the same time. Consequently, when data retrieval requires several bus cycles, the processor remains idle, further reducing its ability to perform instruction-intensive AI tasks. Tasking: when the brain performs a task, a number of synapses fire at one time, allowing simultaneous execution of multiple operations. The original von Neumann design allowed just one operation at one time, and only after the system retrieved both the required instruction and data. So computers today typically have multiple cores which allow simultaneous execution of operations in each core. So if we see here one at a time, so single tasking, and multiple at once, that would be the multitasking. Relying on new computational techniques, we continue with now. So after creating a prototype, a typical setup to perform the tasks required to simulate human thought on a given topic, you may need additional hardware to provide sufficient processing power to work with the full dataset required of a production system. Many methods are available to provide such processing power, but a common one is to use graphics processing unit, so GPUs, in addition to the central processing unit of a machine. So here we will describe and address the GPU issues. Now, the von Neumann bottleneck is a natural result of using a bus to transfer data between the processor, memory, long-term storage, and peripheral devices. No matter how fast the bus performs its task, overwhelming it is always possible. Over time, processor speeds continue to increase while memory and other device improvements focus on density, the capability to store more in a less space. Consequently, the bottleneck becomes more of an issue that every improvement causing the processor to spend a lot of time being idle, so waiting. Within reason, you can overcome some of the issues that surround the von Neumann bottleneck and produce small but noticeable increases in application speed. Here are the most common solutions. Caching. When problems with obtaining data from memory fast enough with the von Neumann architecture became evident, the hardware vendors quickly responded by adding localized memory that didn't require bus access. This memory appears external to the processor but as part of a processor package. High-speed cache is expensive, so cache sizes tend to be smaller. Processor caching. Well, unfortunately, external the problem is that external caches still provide insufficient speed. Even using the fastest RAM available and cutting out the bus access completely doesn't meet the processing capacity needs of the processor. So processor caching involves small, high-speed memory, so L1, L2, and 3 caches built into the CPU to quickly access recently used infrastructure and data. The next step in making processors work faster is to guess which data the application will require next and load it into the cache before the application requires it. Using specialty RAM is the next here. While employs faster or parallel access memory types like SRAM or HBM, and you can get worried by RAM alphabet soup because there is DRAM, there is HRAM, so a lot of RAMs. Anyway, in most cases, the improvements resolve around the idea of getting data from memory and onto the bus faster. Two major factors affect the speed: memory speed and the latency. Memory speed, how fast the memory moves data, and the latency, how long it takes to locate a particular piece of data. As with many other areas of technology, hype can become a problem. For example, multi-threading, you see here, the act of breaking an application or other set of instructions into discrete execution units that the processor can handle one at a time is often touted as a means to overcome the Neumann bottleneck, but it doesn't actually help the bottleneck. Multithreading is an answer to another problem, namely application latency. So making the application more efficient. When an application adds latency issues to the von Neumann bottleneck, the entire system slows down. Multithreading ensures that the processor doesn't waste yet more time waiting for the user or the other application, but instead has something to do all the time. Application latency can occur with any processor architecture, not just the von Neumann architecture. Even so, anything that speeds the overall operation of an application is visible to the other user and the system as a whole. So we can now continue with defining our GPUs. The original intent of GPU was to process image data quickly and then display the resulting image on screen. During the initial phase of PC evolution, the CPU performed all the processing processing, and which meant also that the graphs or graphics could appear slowly while the CPU performed other tasks. During this time, a PC typically came equipped with a display adapter, which contains little or no processing power at all. A display adapter merely converts the computer data into a visual form. In fact, using just one processor proved almost impossible after the PC moved past text and only displays or extremely simple 16-color graphics. However, GPUs did not make many inroads to computing until people began wanting 3D output. At this point, a combination of CPU and a display adapter simply could not do the job any longer. So we moved into the first direction as with the HW 4860, which included a CPU and a special graphics chip, that's 8060 in this case, on the motherboard. This 8060 chip provides the benefit of performing calculations extremely fast. Well, unfortunately, a multiprocessor like this, asynchronous systems, did not quite meet the expectations that people had for them. And of course, they were also very expensive. A GPU moves graphics processing from the motherboard to the graphics peripheral board. The CPU can tell the GPU to perform a task, and then the GPU determines the best method for doing so independently of the CPU. A GPU has a separate memory, and the data path for its bus is immense. In addition, GPU can access the main memory for obtaining data needed to perform a task and to post results independently of the CPU. Consequently, this setup makes modern graphics displays possible. Okay, so we see the features here: dedicated memory, high band data path, and also it can access main memory for data and results. So what truly sets apart a GPU is that a GPU typically contains hundreds or thousands of cores, contrasted with just a few cores for a CPU. 8 cores is about the best that you can get, even with the newer i9 processor. An A100 GPU can host up to 80 gigabytes of RAM and has up to 8,192 FP3, so single precision floating point format, CUDA, so Compute Unified Device Architecture cores. So again, 8,000, right? Cores per full GPU. Now, CUDA or Compute Unified Device Architecture is a parallel computing platform and application programming interface API developed by NVIDIA. Even though the CPU provides more general purpose functionality, the GPU performs calculations incredibly fast and can move data from the GPU to the display even faster. This ability is what makes the special purpose GPU a critical component in today's system. So GPU is beneficial only because it can perform matrix multiplication quickly and on a massive parallel level. Researchers constantly struggle to discover better ways to train, verify, and test the models used to create AI applications, so the models. And here we come to working with deep learning processors, so DLPs. One of those ways is to use new computing techniques, as described in this section relying on new computational techniques earlier here. Another way is to throw more processing power at the problem, such as by using a GPU. However, a GPU is beneficial only because it can perform, as we already talked about, matrix manipulation quickly and on a massive parallel level. Otherwise, using GPU can create problems as well. So the search for something better is ongoing, and you can find a veritable alphabet soup again here, like CPU, GPU, APU, TPU, VPU, APGA, and QPU. But let's define first the DLP, a deep learning processor. It's actually a specialized processor that provides some benefits in training, verifying, testing, you see here as well, running AI applications. They try to create an environment in which AI applications run quickly, even on smaller, less capable devices. Most deep learning processors follow a similar pattern by providing separate data and code memory areas, separate data and code buses, specialized instruction sets, large on-chip memory, and large buffers to encourage data reuse patterns. Now, since these first experiments with DLPs, the number and the types of DLPs have soared, but most of these endeavors are now part of the university research effort. The exception are a neural processing unit, so NPU, created by Huawei and Samsung for mobile devices, and the tensor processing unit, so TPU, created by Google, specifically for use with TensorFlow. These two DLP types are described now. So we start with the mobile neural processing unit, NPU. A number of mobile devices have neural processing units, NPU, in addition to the general CPU to perform AI predictive tasks using models such as artificial neural networks and random forest, so RF. You cannot use an NPU for general computing needs because it is so specialized. However, an NPU characteristically performs up to 10 times faster than a GPU does for the same task. An NPU is specialized in the following ways. So it accelerates the running of predefined models as constructed to training, verification, and testing. It is designed for use with small devices. It consumes little power when contrasted to other processor types, and it uses resources such as memory and efficiently. So, because the precise boundaries between processor types are hard to find, you might see a number of NPU look-alikes or alternative classified as NPUs. However, there is a list also that you can currently classify as true NPUs. Ali NPU by Alibaba, Asken by Huawei, Neural Engine by Apple, Neural Processing Units, so NPU, by Samsung, and also there is one by Intel, and NVDLA is by NVIDIA. Well, let's continue with the Tensor Processing Unit. Google specifically designed the Tensor Processing Unit, so TPU, in 2015 to more quickly run applications built on the TensorFlow framework. It represents a true chip specialization in that you cannot use it effectively without TensorFlow. However, it's different in another way in that it's an application-specific integrated circuit, so ASIC. So one more time, application-specific integrated circuit, rather than a full-blown CPU-type chip. The differences are very important here as well. An ASIC, so application-specific integrated circuit, can perform only one task, and you cannot change it. Because of its specialization, an ASIC is typically much less expensive than a CPU. Most ASICs, so most application-specific integrated circuits implementations, are much smaller than the same implementation created with a CPU. Compared to a CPU implementation, an ASIC is more power efficient. An ASIC is incredibly reliable. Continue now with the specialized processing environment. Deep learning and AI are both non-von Neumann processes, according to many experts, including also one CEO, which is not that important right now. So I continue with the increasing hardware capabilities. That's more important. The CPU still works well for business systems or in applications in which the need for general flexibility in programming outweighs pure processing power. However, GPUs are now the standard for various kinds of data science, machine learning, AI, and deep learning needs. Certainly, developers are constantly looking for the next big thing in the development environment. Both CPUs and GPUs are producing, both CPUs and GPUs are production level processors. Production level processors. In the future, you may see one of the two kinds of processors used in place of these standards. So, application-specific integrated circuits, ASICs. ASIC solution offers extremely fast performance using very little power, but lacks flexibility at the same time. You can find an example of an ASIC in the form of a TPU as well. Field programmable gate arrays. So FPGA is, as with an ASIC, vendor generally crafts an FPGA for a specific purpose. However, contrary to using an ASIC, you can program an FPGA to change its underlying functionality. An example of an FPGA solution in Microsoft Brainwave, which is used for deep learning projects. The battle between ASICs and FPGAs promises to heat up, with AI developers emerging as the winner. Okay, looking at the future AI hardware, the new two areas of advancement in hardware capabilities, so neuromorphic computing and quantum processors. These cutting-edge technologies can potentially improve processing efficiency and capability, pushing the boundaries of AI also very quickly. Let's see now something about advancing neuromorphic computing. So neuromorphic computing is the field of technology that mimics the neural structure and operation of the brain. It uses specialized hardware to create more efficient and adaptive AI systems. These chips can handle complex tasks like pattern recognition, sensory processing, and real-time decision making, with significantly lower energy consumption than the traditional processors do. Neuromorphic systems often utilize spiking neural networks, so SNNs, which process information like the brain through the timing of spikes rather than continuous signal transmission. This approach allows for more efficient and faster data processing, especially in applications that require real-time analysis and adaptive learning. Autonomous drones and robots can benefit from neuromorphic chips by enhancing their ability to navigate and respond to their environments. Now, quantum processors represent a big leap in AI hardware capabilities. Unlike classical processors that use bits to represent data as zeros and ones, quantum processors use quantum bits, so qubits, which can exist in multiple states at the same time. This unique property allows quantum processors to perform certain calculations much faster than classical computers do. So companies like Google, IBM are making strides in developing quantum processors. With regard to AI, quantum processors have the potential to revolutionize optimization problems, enhance machine learning algorithms, and accelerate complex simulations. Quantum computing is still in infancy, but we will see how quickly it can move on and basically improve. Well, let's see the integrating advanced specialized sensors. An essential component of AI is the capability of the AI to simulate human intelligence using a full set of senses. Input provided by senses helps humans develop the various kinds of intelligence as well. Human senses provide the right sort of input to create an intelligent human. Even assuming that it becomes possible for an AI to fully implement all 8 kinds of intelligence, it still requires the right sort of input to make that intelligence functional. Humans typically have 5 senses, so sight, sound, touch, taste, hearing. Oddly enough, humans still don't fully understand their own capabilities, so it's not surprising that the computers lag when it comes to sensing the environment in the same way humans can do. For example, until recently, only 4 elements comprised taste, so salty, sweet, bitter, and sour. Recently, two more tastes now appear in the list: umami and fat. The use of filtered static and dynamic data now enables an AI to interact with humans in specific ways. For example, consider Alexa, the Amazon device that seemingly hears you and then says something in response. Even though Alexa doesn't actually understand anything you say, the appearance of communication is quite addicting and encourages people to anthropomorphize these devices. To perform any part of its task, Alexa requires access to a special sensor, a microphone that allows it to hear. Actually, Alexa has a number of microphones to help it hear well enough to provide the illusion of understanding. Unfortunately, as advanced as Alexa is, it cannot see, feel, touch, or taste anything, which makes it far from human as well. Let's see integrating AI with advanced sensor technology. Integrating advanced sensor with AI is now changing how machines interact with the world and expanding what they can do. Sensor fusion is the first one of the key advancements. So, sensor fusion integrates data from multiple sensors to help understand environments. For example, combining inputs from camera, light detection, and ranging, so LiDAR, radar, and ultrasonic sensors help self-driving cars navigate safely. Bio-inspired sensors are the next key advancements. These sensors mimic biological systems. Artificial skin detects pressure, temperature, and texture, allowing robots to handle delicate objects carefully. Other sensors can identify smells like chemical compounds, aiding in early disease detection and pollutant monitoring. Quantum sensors are the next key advancements. Quantum sensors are so using principles of quantum mechanisms. These sensors achieve high precision. They can detect tiny changes in magnetic fields, gravity, and temperature. This is important for advanced medical imaging and navigation in places where GPS doesn't work well. Environmental sensors are the next key advancements. So these sensors detect events like infrared and ultraviolet light and radiation, enabling AI systems to operate in tough conditions as well. They are crucial for industrial monitoring and military surveillance. So now we finish with our topic, and we see here that the PC used for Neumann architecture is actually causing problems these days. The von Neumann bottleneck and single points of failure and the inefficiencies cause latency. And this, of course, may bring trouble in the use of AI as well. That's why AI needs more specialized hardware. General purpose hardware becomes insufficient these days. Solutions of the is for the use of are GPUs or deep learning processors, or DPLPs, then specialized processors like ASICs, as we talked about them before. So the application-specific integrated circuits and the FPGA, so field programmable gate arrays as well. So GPUs, graphical processing units, were originally made for graphics, and now they are key in using AI technology. We also learn about the future hardware innovations such as neuromorphic computing and quantum computing and advanced sensor technology. So key advancements in sensors. That's it for now. I would like to say thank you for your attention. I know it's a hard topic, but I hope that you also could be updated and that helped you to find a way. And now we can continue with the video actually, which I just prepared for you. So thank you. Bye. We finished the specialized hardware. I would like to continue with an interesting video, namely to show you how you can build an own AI based on the models you can download from olama.com. Well, I'm going to do that too. You see that DIY AI infrastructure, build your own privacy preserving AI at home. So I'm going to disappear now. That's supposed to be the best idea here, I guess. And let's see the video.
Martin, it seems like AI is everywhere these days. Finally, we have a computer that actually understands my language instead of me having to learn its language. A system that understands me. For instance, what if I'm looking to buy a new car and I need to do some research on the alternatives?
Yeah, you could tell the chatbot to act as a car expert, and then you could ask it what would be the difference in cost to operate a gas-powered car versus a hybrid car versus an EV car, and then get guidance on the decision.
And if it helped me find a rebate from the power company, it could pay for itself in just one instance. And if I enjoyed tinkering and DIY projects, wouldn't it be cool to learn how the technology works and host my very own instance of all of this?
Yeah, very cool. And in fact, we have a colleague, Robert Murray, who has done just that with equipment in his own home office.
Wait, you mean without a server farm of GPUs that dim the lights every time you ask it to do something?
Absolutely. So let's bring him in to tell us how he did it. Today, requests to generative AI typically connect to an AI model hosted somewhere on a cloud, but Robert here has built an infrastructure to host AI models like Llama 3 and IBM's Granite on his own personal infrastructure. So, Robert, I want to understand how you did this.
Absolutely.
So let's start with this box, which represents your computer at home. So tell me sort of the stack that you built here.
Sure. So I started with Windows 11.
All right, so just a straight old...
Because I have it.
Yeah, okay. That was the reason, just
Yes.
because it's there.
It's there.
Okay, so you got Windows 11, and then what's on top of that?
Well, I unleashed WSL2.
Now you're going to have to tell me what WSL2 does.
It's basically Linux on Windows.
I'm going to think that there's probably a virtualization layer coming.
Yes, there definitely is, and that is Docker.
Okay, Docker is running on top of all of this. Now, we need some AI models. So where did you get your AI models from?
I pulled them down from olama.com.
Okay, so if we take a look at the AI models, what are some of the models that you actually took?
Well, so I started with Granite,
Right, IBM's Granite model, yeah.
Llama,
Okay.
and there's so many other models that you can pull down.
Yeah.
They're there, open source.
A whole bunch of open source models. Okay, so we've got a Docker machine here with Windows 11, WSL2. You've downloaded these models from Olama. Is this now the solution?
Well, I actually can use this. I can run all this right from the command line.
Wow, okay. So you can open a terminal window and then start chatting with Llama or Granite that
Yes,
way.
very, very fast.
But most of the AI models that are cloud hosted, you do that on a chat interface, a UI. So how are you able to add a UI to all of this?
Docker containers.
Ah, okay. All right. So let's put some Docker containers in. What did you have for the UI?
I used Open Web UI. It's one of the many solutions that a person could use, but I found this to be extraordinarily helpful.
Okay. So with
And easy to use.
Yeah, so with Open Web UI, you can just open up a browser and then chat with the model, pick the model that you want, and send requests to it.
And there I was, and that's what I was working with for a long time right out of my home.
But what if you're on the go?
Well, that's where another container comes in.
Okay, what have you got here?
So it's a VPN container configured with my own domain.
All right. So what can access this guy?
This.
Okay, your phone.
So now I am able to access my system from my phone or basically any internet connection. It's awesome.
How very cool. All right, well, let's say that I wanted to actually replicate what you've done here and build it. I'm going to ask you about this server itself. What are the system requirements? So let's start with RAM. How much RAM do I need for this?
Well, I would recommend at least 8 gigabytes.
8 gigabytes, that's not much. How much do you actually use?
Well, I'm using 96.
Okay, slightly above the minimum requirement.
Absolutely.
All right, so that's RAM. What about storage?
Storage, I would recommend having at least 1 terabyte.
Okay, because some of these models can get pretty big, right?
Yes, they can.
Now, these models come in different sizes. So what parameter count sizes were you using with Granite and Llama?
I'm using anywhere between 7 and 14 billion parameters.
7 to 14 billion. Okay, so that is...
I have run up to 70.
70. How did that work out?
Slow.
I can imagine. Okay. So the other thing that people often talk about in terms of system requirements are GPUs. So should I be using GPUs with this solution?
Well, my initial configuration, I had no GPUs. But more GPUs, the better.
The more the better, right. So we've got this self-contained solution now, and it's got me thinking that when I talk to a large language model, I often want to provide it documentation in order to chat with that document.
Absolutely.
Now, if I'm using a cloud-based model, I need to take my document and upload it to somebody else's server so that the AI model can see it. I take it that you have a better solution to that.
I do. I use my own NAS system.
Okay, so you have a NAS server set up.
And from that NAS system, I pull in my documents, pull them into the Open Web UI, and chat away. And I'm doing it every single day.
So, Robert, the other thing I like about this architecture is, at least to my mind, this looks like a really secure solution.
Hold the phone there just a second. Nice job, AI guy, but let's really look at the security on this, Robert. First of all, I think it is a good job here, and I think you've put in some features that will help preserve security and privacy. But let's take a look at what some of those are, because what you don't want is your data is our data. We want your data is your data. Not your data as our business model. So how do we make sure that we're not falling into the same trap that a lot of those other chatbots that are free apps on the App Store that you can download aren't falling into?
Well, first off, I put it on my own hardware.
Yeah, exactly. So I see that very clearly. It's on your hardware, so you control the infrastructure. You can decide when to turn the thing on and off. It's your data on your system. So that's the first point.
Absolutely.
Yeah, and then also it looks like that you included a private data store. So now it's not your information is training somebody else's model and you're pulling information that might be poisoned or anything like that. You have some control over that as well.
Yes, and interesting enough, that's what's actually got me started on this whole path. By having an NAS, I wanted my data to be my data.
Sure. And data is the real core of an AI system anyway, so that makes a lot of sense. Also, I noticed some open source components. So you've got one right here. You've got open source models here as well. And that's a good idea because instead of proprietary stuff, in these cases, at least we have an idea that the worldwide open source community has had a chance to look at this and vet it. Now, granted, there's a lot of information to be vetted, so it's not trivial, no guarantees, but maybe it's a little more secure because more people have had a chance to look at what's actually happening under the covers.
Agreed.
Yeah. And then also, I notice you want to be able to access this from anywhere, which is one of the really cool aspects. And we want to make sure that that access is also secured. So I see you put a VPN over here so that you can connect your phone in and do that securely. And how are you making sure everybody else in the world can't connect their phone in here as well?
Multi-factor.
Okay. Multi-factor authentication, and now we know it's really you, and we know the information is exchanged in a secure way. So a lot of features that you put in here. I think it's a nice job.
Thank you.
Yeah, and one other thing to think about, because these components, we really don't know what all of them would do, it is still possible that one of these things could be phoning home and sending data to the mothership, even without your knowledge. So one of the things that might be useful is put a network tap on your home network, and then that way you could see if there are any outbound connections from this, because there shouldn't be based upon the way you've built that.
Well, that's a really great idea, Jeff. I'm going to have to look into that.
Okay, there you go with the improvements for version 2.
Hey, Jeff.
Oh, hey, Martin. Nice to have you back. Yeah, it seems like Robert's really done some nice work with this, don't you think?
Yeah, for sure. It just goes to show that you can now run sophisticated AI models on a home computer to build a personal chatbot.
Yeah, something like that would have been science fiction just a few short years ago, but now it's available to anyone who really wants to spend the time to assemble it all.
Right, and you learn so much more about a technology by really digging into it and getting your hands dirty with it.
Yeah, and by the looks of your hands, you've been doing a lot of digging because those things are filthy. And the added bonus is that you end up with a better assurance that your data is your data because you have more control and you can ensure that privacy is protected in the process.
Spoken like a true security guy that you are, Jeff. All right, so you've seen Robert's approach. So how would you, dear viewer, do anything differently to make the system even better? Let us know in the comments.
Well, no, this was exactly the correct video that you should have watched as well. And not only I say it, but many people, I mean, if you check the comments here, you will also find out that many people are very, very thankful for this DIY infrastructure that helps people to build their own infrastructure for AI or using the models from llama.com, which are uploaded there. And again, make sure that you, when you are interested, build a bigger one. Also use GPU if possible. Of course, it depends on your budget. Me, myself, I'm not going to be able to use a GPU at the first moment as well, because I'm going to try it out by myself as well. So that's it for now. Thank you very much for your attention and see you the next time. Bye for now.
That was the